Let's start. Today I will going to talk something about logistic regression. Here's the outline of today's presentation. I will give a brief introduction about logistic regression and talk something about algebraic linear regression and introduce the logistic regression. Here is the introduction. In the machine learning area, regression is one of the supervised learning techniques, where we have a bunch of data points and their corresponding labels. Here, each data point can be a scalar or a vector, and the label is usually a scalar. And here is the example of a training size. Is a pair of input variable and the target. And then the goal of the regression is to predict the label T of any given new data point X based on what we have learned from the training data. And I will give a quick review of what's the ordinary linear regression, since that it has been talked many times in our meeting. And the linear regression is a linear combination of input variable. It can be expressed as the y of x and omega equal to a linear combination of input variable. And here x can be a d-dimension variable. And we can extend this simple equation to a more complex form. For example, we can use a nonlinear function to work on the variable x. Then we can still have a we still have a linear combination of nonlinear function. And so the problem is what is y? Y is a regression function. We suppose this function is a linear combination of input variable or a linear combination of some nonlinear function. This nonlinear function works on the input variable x.
And
W is some weight. It's the model parameter. The problem is we want to obtain the model parameter W. So how to get the model parameters? Here we have some assumption. Suppose T is the label, and it's equal to the regression function output plus noise epsilon. And here y is the regression function. It's a deterministic regression function, and we suppose the arrow epsilon satisfy a Gaussian distribution with zero mean and variance like sigma square. So why we have this assumption? Because the output of the regression function maybe have some error, so it's not it cannot exactly recover the label. So there are some error. Another case is if T has some outlier, it's far from the regression curve, so there may be also introduce some error. So this epsilon can model the error between the regression output and the original label. And why we assume the regression error is satisfied Gaussian distribution is according to the central limit theorem. If we have a independent variable and we have enough number of this random variable, then we can assume the distribution of those variables satisfy a Gaussian distribution. this comes from the central limits theorem. And given this assumption, how can we find the model parameter? We can use the maximum likelihood algorithm. So as first, take a look, we'll select likelihood function of this problem. For a single point, for a single data point, we can express the likelihood function as this. It's just the Gaussian distribution with mean given by the regression output function y and the variance sigma square comes from the arrow. And we give a filter assumption, each data point is independent. So in this case, the likelihood function based on the whole training data can be factorized like this. So it's the product of all the individual likelihood. Here T is a vector, is the set of all the training label, and X is set of all the input variable. And since directly maximize this likelihood function is not easy, so we take algorithm of the likelihood function, then we can minimize the maximize the algorithm of the likelihood function is equivalent to maximize the original likelihood function. And since we assume the regression function y of x and w satisfy this linear combination of some nonlinear function of xn, and the Gaussian distribution is given in this form. So we plug in those two terms. We pass those two terms into the algorithm of the likelihood function. Then we can express the algorithm of the likelihood function like this. And the sum then we can see the first term of the logarithm likelihood function is constant. It only depends on the sigma square. It does not depend on the model parameter W. So by maximize this log likelihood function is equivalent to minimize the second term, and we can further define the second term as a sum of square arrow function like this. And then we try to minimize this sum of square arrow function. And to minimize this arrow function, we just need to take first order derivative of this function. If we take first order derivative, we can have the following equation. And we set the first order derivative equal to 0. Then we can get the closed form solution of the model parameter W. And finally, we can express this like this matrix form. And here the matrix capital Phi is called the design matrix. A form of this form. This is just a quick review of what's the ordinary linear regression, and it has been talked many times by many people in this meeting. So now we will go further to talk something about the logistic regression based on what we have talked about the ordinary regression. And here. So the logistic regression is used in classification problem, and we can also use the linear regression in the classification, but they have some problem. For example, suppose we only consider a binary classification problem. So So the label can only be 0 and 1, since we can consider a binary case. And suppose we have input variable like x here. So if we have a bunch of observation x and their corresponding label t here, if we use the linear regression, we try to fix line like this, then we can give some threshold with classified. For example, this is t equals 1, and this is t equals 0, and this is x, this is t. And we can give some threshold like a point about this point are classified as 1, or below this point is classified as 0. But the traditional linear regression model is very sensitive to the outlier. For example, if we have some point here, and we try to use linear regression, then the curve will be something like this. So there are a lot of misclassification classified point here. So one way to avoid this problem is use logistic regression. And let's see here. Suppose we have a function y of x, and w is a linear combination of equal to x, and here x can be phi x. For the use of exposition, we only use x here, and this is the ordinary linear regression, and the output y can be any real number, and if x goes to infinity, then y also goes to infinity, something like this. So one way to make sure we can bound the output within a region, for example.
Why Deriving transforms? Deriving transforms?
Yeah, Deriving transform. But here we only consider the common factor.
Oh.
So each factor is a common factor. So there's suppose we want to find the output within a certain region, for example 0 to 1, for our classification purpose. So in this case, we can use some function to transfer the output of original linear function to another, and then we can make sure the output is within 0 and 1. So the problem is how to choose this function. I will give you the function first, then explain why we choose this function. It can be, this function can be something like this. So usually this function called Sigmoid function, our logistic function. And the property of this function is something like this. This is for example, we have a function, and this equal to 1 plus 6. So here is c, here is the g of c here. And if we plot this function, then we can find out this function is something like this. The maximum value is less than 1, and the minimum value is larger than 0, and when z equal to 0, then the g of 0 equal to 0.5. So there are some nice properties. The first one is the output of this function is between 0 and 1. and this function is symmetric. And for any input C, the output is bounded by the 0 and 1. So this is nice property, and we can use this property in our classification problem.
So, what does it show? The G function, what does it show? The G function?
This you mean by it?
No, for the GWTX.
Oh, suppose. What do you mean? You can set Z equal to.
No. I mean that why you use G and apply the GWTX? What does it mean? The GWX?
Oh, this is from here.
Yeah, I
So
know.
in the original linear regression, we have the regression function of this function.
Yeah.
The output of this regression function is infinity to negative positive. It can be anything.
Yeah, I know, but yeah, my question is that you have the GWTX, okay? Yeah. Why do you want to use G?
Why? You can use H. It's just
No,
it's
I
no
mean,
problem.
why use this function?
Why I use the function? Yeah, I will talk to you later. I already said I just gave you this function, then I will explain why I use this function. So I already talked something about the property of this function. It's between 0 and 1 is symmetric, right? And there are two ways to expand your patterns. The first way, let me see. For example, here we have a t can be 0 and 1, right? So if we have a training side, maybe capital T, and T1, T. So the probability of T equal to 1, and is expectation of T1, and the probability of T equal to 0 is just 1 minus T equal to 1. So we just think T is equal to the probability T equal to 1. So we can define the O's here. Also the definition of O's is P over 1 over T. P over 1 minus over T. So this is the definition of O. And the property of O's is not symmetric. So for example, if P equal to 0.9, then 0.9 over 0.1 is equal to 9. If P equal to 0.1, then it's 0.9 over 1 over 9. So it's not symmetric in this case. If we want to use a binary classification, we hope the output is sometimes symmetric, because this is the probability of one T equal to 1, and this is so this is the probability of T equal to 1 equal to 0.5 in this case, and this is the probability of T equal to 0, 1. In this sense, they are symmetric, right? So we hope the output is also symmetric. So in this case, it's not symmetric. So what can we do? We can take an algorithm of the O, then we can find the is equal to minus. So in this case, the output is symmetric. So they are all on the same scale. So this is so we call this function like a logic function here. And if we want the output of linear regression equal to this O's, equal to this large functions, you can set something like this, right? If we solve this equation, we can find this is the Sigmoid function. So this is one way to explain why we choose this function. They came from the old. Since the old is not symmetric, so it's an algorithm. So then we can calculate what's the p here, then we get the logic function. So another way to explain why we choose this function is from the exponential family. So we can see P here is a binary value, right? So it satisfies Bernoulli distribution. So in Bernoulli distribution, we can express P equal to 1 given something. It's is equal to P as we defined, and P equal to 0 is equal to 1 minus P. So we can combine those together with the compact form P given x equal to P minus Q1. If P equal to 1, this function equals to P. Otherwise equal to 1 minus P. So this is the Bernoulli distribution. So if we express this Bernoulli distribution in the exponential family form, so what's the exponential family? Suppose we have a function like this. So we keep here x is a variable. It's not an observation here. And this is the exponential family. We are going to solve. And x given some parameter state. So in the exponential family, we have a variable x and some parameter state here. And it can be expressed something like this. So this is a function of x. So this is some parameter theta, and this is a sufficient statistic. It's a function of x, and here is another function of theta. So any distribution, if they can be expressed in this form, what's v? What? Theta.
Theta also.
Theta. Oh, theta is some parameter.
Oh.
It's the parameter of your distribution. So for example, a Gaussian distribution, we have mean and the Arvinstein parameter, and x is the variable. So for any distribution can be expressed in this form, you can call this distribution is belong to an exponential family. So we can express the Bernoulli distribution also in the expression exponential family form. It can be we take an exponential here, and here's p. So in this case, we can use p as one random variable here. And here's p, yeah, p. So we take the exponential of this equation we got. And if we maximum likelihood with respect to this distribution, we will find something like this. Yeah, so for any distribution belongs to exponential family, we can do something like this. So we can figure out which function we need to do generalized regression. So we call the reverse linear regression an ordinary regression, since it's just a linear combination of input variable. So we call the generalized regression. We use some function on the output of the linear regression. Then we can get some generalized linear regression. And how to choose this function? You can get some hint from the exponential family form of this distribution. And so since I already convinced you we can use this function to do some regression. So we just need the maximum of this function. Right? So what's the maximum function? For example, we have t. Here the capital T is a set of training data, of training label. And given some capital X is the size of training input variable, and some model parameter here. And we can express this as I given as I, and some model parameter here, and I is from 1 to n. Suppose we have any number of observations. So this is the equilibrium function, right? I maximize this function is not easy, so we take a algorithm since our function is convex and monotonic. So it's equivalent to max maximize the algorithm of this P. So if we take algorithm, this is the symmetry here. And here is the Bernoulli distribution, so it's
this should be a logistic regression function. That part should be a logistic function.
Yes, this should be a logistic function. H. This G. In this case, we can use H. H here. So we have H of only X. And we use this notation. Here, H of Cn is equal to H of here. We use the substitution here. And 1 minus H Cn here. So this is a mechanical function. And we can get Tn Cn plus 1 minus Tn and we define this term as arrow function at the original linear regression function. And we try to maximize this function. So we just simplify and take first order derivative with respect to all the parameter only and set it equal to 0. So we can see the derivative of this function is equal to the derivative with respect to H Z. Also derivative with respect to Z. Also derivative of Z with respect to I. So they can be decomposed by the product of those three terms. So as we see, what's the first term here? Maybe and here. So we pick first order derivative with respect to H. It's just the first term is Tn over H Cn, and the second term is 1 minus Tn over 1 minus HCn. Right? And for the second term,
is there a minus sign? Because if you derivative of
Assumption.
oh, this is oh, yeah. And for the second term,
That's equal R. T equal to R.
oh yes, Ti. So it's H. Yeah, if we take this from out, and we got and also so we got the second term, and for the third term, we have freedom with respect to the V. It's just axis. That's all. Yeah, it's x because here omega is the row vector, and here is x. So
Omega transpose is the omega is
yeah, omega is the common factor.
yeah.
So it's the pizza. Because we take the bracket row vector now, which is transpose. Yeah, it's not a team view.
Yeah, transpose.
So we got this term, this term, this term. Oh, here's the and so we just get everything together. T over H. Expand this term, and this term cancel this term, so we got I and this term cancel this term, we got minus HCI, 1 TI, and x here. And finally we got TI here, and the TI times HC minus was cancelled by this second term because there are minus and minus here. So finally we got something like this. So we have one. Yeah, this is yeah.
I mean, it has a
yeah,
sigma for all of them? For the sigma? Has a sigma for it?
Sigma.
It's R sigma? Or no?
Sigma.
Oh,
No.
just for the each of?
Yeah, just
each
for
of
the E. Just for the E, we have
What
the
is
sigma.
CI? Just CI?
Yeah,
And
just
for the
I.
each of?
Yeah. And if you take a look at the solution here, this is the solution of a Gaussian distribution. It is also known as the lattice square. We can see they are quite similar. Both of them are pi minus something and times all equal. Right? The only difference is in the lattice square equation. We have the function like t transpose times phi x. Here is the h of this function. So we can put something like this. H p x here. And so this function makes sure the output of the linear regression is bounded between 0 and 1. So we can use this function for the binary classification problem. And we can also generalize.
Can you say it again? As it's between 0 and 1?
0 and 1.
Okay, so can you use that for the classification?
Yeah, for the binary classification. So we can also generalize this equation into exponential families of different distributions. So we can choose different functions here.
Yeah.
So this is the idea of regression for different distributions. And specifically this is for the logistic regression, and this is for the linear regression. This is also called lattice square. So you can also use other distributions like Gaussian or multinomial and gamma, something like that. You can generalize your regression algorithm. Yeah, depends on the distribution of your label. In this case, the distribution of this label satisfies a boundary distribution. So we get the logistic regression. So in that case, it was modeled as a Gaussian distribution. So we got the latest square model. So I name